Hello,
Hello.
my name is Shemi, and this is my podcast, The Miracle of Abstraction. Today, my guest is Krystal Guo,
Hello.
and she's a mathematician and an assistant professor in discrete mathematics at Kordewijk de Vries Institute for Mathematics, KDVI for short, at University of Amsterdam. Thank you for being here, Krystal.
Thank you for having me.
Yes. So every episode we begin with the same question. What is the last thing that you learned and you went, whoa, in mathematics or not?
Wow, okay, this is Yeah, so there was a math concept that came up in a master's project that I'm co-supervising with Ferenc Spence. And it's called the spectral center of a tree.
Okay.
So it's a bit area specific, but you have graphs. I don't know if your audience is familiar with graphs, but they
I
are
don't know either.
some structure where you have some vertices, some of which are connected via nodes, kind of like Facebook, that you have people and then you have an edge between them if they're friends.
Okay.
And it's a mutual relation, not like X, where it's a one-way, you
Okay.
follow them, but they don't follow you type of
Okay.
possibility. So, so in such a network, you can study it using its eigenvalues in some way.
Okay.
And in sort of the big picture, it's used in many things. For example, Google's original algorithm for back when we were owning a search engine.
Okay,
In
so back
what-
from 90s.
Yeah, like in what order are they gonna return you the websites that are relevant to your search?
Yeah,
How do they do this? Well, they just made a very large directed graph.
how
and
they
that-
used to do it.
Yeah, how they used to do it. But people have been like trying to hack the algorithm. So now it's a
Okay.
very refined algorithm that is only loosely based on this.
Okay.
So what they did is they just take the adjacency matrix of the network that
Okay.
they do have of things linking to other things. And now it's a large matrix. They compute the first eigenvector,
Okay.
and then they just return the links based on how big the value is in the eigenvector.
Okay.
This is the PageRank algorithm. It's like the original
Okay.
thing. So it's like the beginning of, you have these networks, which we call graphs, and then a reasonable way to study them is not to just look at each of them, which is too much information, but to compute some eigen information about the graph, some eigenvalues and
Okay.
eigenvectors, and use this to do
We
stuff.
compute some eigenvalues, stuff, that's how we do it.
Yeah.
And what happened in this project?
So in this project, the student and Ferenc, they found some resources, some theorem that appears in a book, and so it's in the book of Brouwer and Hammers called
Okay.
Spectra of Graphs, and this idea kind of only comes from a paper, I think, by the same author. So they really came up with it. It's not in an older textbook or anything. And it's the center of a tree. Like, if you have a network, what would you say is like the middle part of it? Is the most essential part of it.
Okay.
So for the tree, a tree is a thing where if you remove any vertex, it becomes disconnected. And it has as few edges as possible, such that it is still connected. So, there are many concepts of what should be the center vertex of a graph or central vertex of various things. And
Okay.
the student is looking at many of them. And
Okay.
the surprising thing is they came up with this definition, which only works for trees, which is that you remove the vertex and it approximately. It's more rigorous than this, but it's that you remove a vertex or set of vertices such that it decreases the first eigenvalue the most
Eigenvalue of the whole graph?
of the whole graph.
Okay. Okay.
So, it's more technical. Don't want to go into the details, but
And
it
there's
was
always-
surprising that you can always.
That this thing exists for the trees.
Yeah,
it was a
it's always an
discovery-
edge or a vertex, and it behaves kind of strangely.
That's interesting, indeed.
Because you would think that there's the tree. Maybe you would think the reasonable definition for the center vertex is the thing that's like in the center, the closest to all the one that minimizes the sum of all the distances to the other vertices. And that is a notion of center. There's also like
So someone like the most likable person in a group of friends.
that would be
Something
that
like
would be a
that?
different thing.
That would be different thing.
Yeah, this is like a location you have to pass in order to go anywhere else.
Yeah.
Yeah, like you would think that's the center. And it would coincide with the most popular person, maybe. But this is like a different definition, and sometimes it is that. Sometimes it does coincide, and sometimes it doesn't. And the fact that
there are
it
multiple
moves,
sensors for different reasons and different purposes.
Yes.
Okay, and
And
then
this one
for
was-
trees, there is this magical thing that was discovered during this project.
Well,
Which-
we discovered it for ourselves, but other
Okay.
people discovered it.
Okay.
They have known about it
That was
in
your
the field.
local discovery,
Yeah, locally
but not
we
global
discovered
discovery
it,
in the whole
yeah.
mathematics.
Yeah.
Okay, but it's still fascinating to have another thing that is kind of stable notion to point at and see like, okay, I have this problem about trees. Is this sensor interacting with this problem?
Yeah, so that's what we're doing.
Oh,
And it appears that it doesn't interact with a lot of problems. The authors defined it for a very specific scenario, and then in their book they even find an application for it. But it's kind of been like been put there to sort of tie this in, but it's not as well connected to the rest of math. But it's a very nice idea. This paper has 0 citations.
what?
Except, I
but
guess,
it is in
by
the
this
textbook, so
book,
the
yeah.
textbook cites it.
I guess, yeah.
It doesn't count as a citation if it's in the textbook cited?
I don't know. Ferenc found 0 citations, but maybe he meant that there were no follow-up papers.
Okay. That's
But
that's also another
we were
woe.
very
That's
surprised.
another
We were
woe
like,
to
oh,
have.
this is like such a, like the way
That's
that
niche.
it's defined.
That's niche.
Yeah, the way that it's defined is like very different from the other definitions, and it's also not that it's just secretly the same as one of the other ones, and that there were very nice facts about it, and then there were nice theorems about it, and the fact that no one knows about it has no citations. The whole thing was very surprising.
So something like a local a peculiarity, like
Yeah.
we noticed that, and like, well, it's stable, it's here, like, but we don't know what to do with this really.
Yeah, it kind of feels like the authors did have this
Okay.
reaction. They were
That's
like, "Oh, look,
fascinating.
it's you can compute it in."
It's
in
like going
these
for a walk
things."
and finding like a magical pebble that is one of its kind. And
But
like,
then you don't know what to do with
what
it.
to
You're
do
like,
with
"I don't know."
something that is one in its kind, and
Yeah,
and discovered out of the context of some problems, probably.
yeah.
That's fascinating. It is a good question and probably good idea to ask this, because we already talked a lot about networks, graphs, eigenvalues, and all of this is about a structure that is a graph, which is like a set of dots connected by some arrows.
Yes. Some edges with arrows or not.
With
Usually
arrows or
without
not.
arrows.
Usually without arrows.
Yes.
And like at the face value, if you look at it, it's like it doesn't look very profound or strong or interesting. So
But it is very
how-
general.
Yeah. So how this very simple thing is like interacting with the rest of mathematics, how is it interesting to study?
Yeah, so it actually interacts with a lot of areas in math. Yeah, so first of all, it has like a lot of interactions with optimization, and many optimization problems are formulated with an underlying graph. And it's like a useful way to store information, to have the interactions between certain things be represented by edges in a graph.
And to like disregard what the interaction really is.
Yes.
To just say there are
is an
these
interaction.
items and there is an interaction.
Yes.
And we actually do not know what does it.
Yeah,
And
maybe.
is that the power of the graphs?
I think the power is that you can now use other techniques or graph theoretic techniques or spectral techniques in my case to solve it.
Yeah.
So for example, everyone is familiar with this coloring problem in
Let's
graph
assume
theory
that I'm not.
class setting.
What's the coloring
that
problem?
You have maps,
Yeah.
like actual maps of places, and you would like to color it,
Mm-hmm.
but you don't have that many different colors of ink because you're like in the 16th century or something. Okay,
Yeah.
maybe 18th century, Euler, and then but you want like countries that border each other. They should get different colors, or else you can't see the border.
Yeah.
Okay, so how many colors do you need?
I believe that I heard that 5 is good.
Yeah, you say you were like, I don't know, but now you know. Okay, it's 4, but 5 is also good. And then the fact that it is 4, that for any map of this form, 4 is enough, was like an open problem for a very long time. And then people solved it, but it's a computer-assisted proof, has gone through many iterations. And in fact, it's not just that this problem is important, it's that it inspired a lot of areas of math. Like many things were developed to try to solve this problem, like chromatic polynomials and other areas and other topics in graph theory. They were formulated just because they would do this. And if you look at these really old, long-standing conjectures from the 80s about graph theory, like when people were laying down the foundations of the field, then some of them also go back to the four-color theorem. That as a footnote, you would, okay, this problem actually arose in that if you would prove this statement and some other statement, then this would imply the four-color theorem. And this is the case for a lot of flow problems. But coloring is a very, it's a very basic problem that comes up all the time. So the easiest way to think about it is you have a graph and there are some connections.
Yeah.
Now you want to assign color so that if there is a connection, they get different colors.
But with the map, I can see the reason why
Yes.
I want to color it.
Exactly.
But other places,
Other
how
things.
do I, other things, or
Yes.
why would I want to color edges connecting other things?
So you can imagine a graph where the vertices are the possible exams that UVA has to hold.
Okay.
And they have an edge if there's a student that has to write both exams.
Okay.
Okay.
So there is a student that like took both classes
Yeah.
and must
Yeah.
write both exams, and now
Yeah.
that's like so.
There's
okay.
some economics class and some math class, and the student that took both of them. And so you would like to schedule the classes, the exams, so that this student could write both of them, not at the same, without any like quantum superposition
Yeah, but
business.
sometimes scheduling at the same time solves a problem. How many exams you have to grade?
Yeah. Okay, but
Which
then
is not kind, but
they have the right to do like a reset. They have to reschedule things anyway. So it would it would save you time in that you wouldn't have to make two versions of the time for the people who
Yes.
write in your slot, and then the 10 students who have this class at the same time who have to write a
Yes.
separate exam. So yeah, maybe the university would not like to economize this, but maybe we think it would be nice if they would assign different times. And so now the colors, they're not like colors, red, blue, etc. They're exam rooms and time slots. So you want to assign an exam room and a time slot
yes.
to every class.
yes, because
But you want to do it to avoid any of these interactions.
because putting a room with a time slot on an edge means
Yeah.
that
on the vertex.
on a vertex means
Means-
that this exam happens here.
Yes.
And
at
then
that
we do
time.
not want to have the same time slot on the
For-
same edge because there is a student, at least one,
Yeah.
who will
Sorry,
say
without the room, just time slot.
just time slot.
Just time slot. Because you could have two exams at the same time, but in different rooms.
But yeah,
Yeah.
you can also have two different exams in the same room at the same time.
Yeah.
Just-
That's
you
just split
see-
the yeah. So
but,
then you
but
have
let's
some other.
disregard that.
But you can also optimize this. That the number of things with the same color, you can also bound this.
Yeah,
This is some
yeah.
other optimization.
So now having two vertices of the same color is to have one angry student coming to you like,
Yes.
I disagree with that.
Correct.
So we do not want angry students.
Yeah, I mean, you could set the threshold higher. You could say, okay, maybe one angry student.
Maybe
where
also
not
with
so,
days, because writing multiple exams
Yeah.
at the same day is also not that nice, or this
Yeah.
day by
But
day.
you can like define, okay, these two courses, when will they have a conflict? They have an edge between them if there's sufficiently many students who will be sufficiently angry if the exams will be scheduled at the same time.
Yeah.
So then you put the edge, these conflict edges. So now you do want to color this graph with as few colors as possible to reduce the amount of time for the exams, and you want a coloring because now it means happy, non-conflicting exams. And this is not just a coloring problem that you can imagine that the university might have to solve. There are larger optimization problems that
I can easily
basically
imagine
are coloring.
with like having this example, I can easily like generalize to places when you have an expert that must go to multiple places
Yes.
to give expertise, but they also have like how many resources
It's a
distribution
resource
is also
allocation
something
problem.
that if you have like a tractor, you cannot have a tractor at two locations at two
Yes.
different times.
Yes.
And sometimes you need multiple things at the same thing, so probably
Yeah.
you have multicoloring there because you cannot construction sites. You need multiple machines
Yeah.
at the same time, so you do multiple coloring with rate of repetitions or so. So that's
Yeah, there are
quickly
many
generalizes to many stuff.
types of coloring problems that.
Whoa!
Yeah.
And now now it's much clear how it like like any fact about graphs can like spread everywhere and improve everything by like 5% in computations, and that's like billions of dollars.
Yeah, yeah. So in optimization, it's not coloring exactly, but you still have similar problems where there is some graph and you just want some substructure that satisfies some stuff, some constraints, and then these general optimization problems model a lot of things, like how airplanes schedule which flights they will run, how the train makes its schedule, which is a thing that people at UVA in the KDVI actually did. Like Schreiber, he actually did work on this.
Whoa.
With the NS trains.
Whoa.
Yeah, there are some really old books in my office that I inherited from someone else that
I know
this
that if one
project.
opens, if one goes through old bookshelves, then
Yeah.
there are like things that like
There's some treasures
how
in there.
did that end up there? Even the question happens. Okay, and your expertise is like in algebraic graphs and graph
Yes.
theory in general.
My expertise is in algebraic graph theory, which is the study of graphs using linear algebra or group theory, and also graphs whose construction is algebraic in nature.
This is far away from my expertise,
Yes.
but I'm curious.
Which is in?
Which is in algebraic geometry, where I just study
Is it
polynomials.
that far? I don't know.
I don't know.
We use a lot of polynomials.
I also use a lot of polynomials, though I prefer to look at the solutions than at them. The polynomials themselves are difficult.
Yeah.
And the spaces of solutions are somehow simpler. But not really.
I see.
So that's complicated. But I'm curious, because that's completely different area. How have you discovered mathematics, and how you, through your journey, went to this particular field?
Interesting question. Yeah, I don't really know.
Was that like a natural, continuous process of like step by step?
Yeah, it's a natural, continuous process. So I went to University of Waterloo in Canada. I don't have a Waterloo sweatshirt, sorry. Where I studied math, and there we have a faculty of mathematics. And at the time that I went there, it had about, 1,500 incoming students in first year of mathematics.
How many? How many?
1,500. Now it's like 2,000
That's a lot of students per
year.
For one cohort.
per cohort.
Ooh.
So the calculus cohort
that's
is
a
like,
lot.
15 sections of 120.
That's a lot.
Yeah.
It's easy to be lost, I think.
Yeah, but because it's a faculty of mathematics, it has multiple departments inside the faculty of mathematics. So it has the department of pure math, the department of applied math, department of combinatorics and
That's a graph
optimization.
itself.
Yeah, the department of statistics and actuarial science, and the computer science, school of computer science.
Okay.
So then it allows you to actually major in multiple things. So that I have two majors in different fields of math. I have a pure math major, and in addition, a combinatorics and optimization major.
Which is not pure math?
No, it's its own department
Okay.
that offers its own degree.
Depending on that department that institutes the labels in that place.
Yeah.
Okay, because it still feels quite pure to me.
Yeah,
As-
but they
as
have like
more-
their own courses. So
Okay.
it's a heavy course load to
Okay.
have done all of this.
Yeah, studying mathematics is not easy.
Yeah.
Anyway, whatever part. Okay, and how through? So you graduated in this too? Two majors.
But yeah, so I did some research projects during my undergraduate mostly in combinatorics. And maybe it's a really nice program that they have there. They have very advanced courses very early. It's hard to say, but I don't know. I just feel like I was naturally drawn to these courses. So you take like a lot of courses.
Okay.
There's a lot of courses, so you get to experience a lot of different math, and then afterwards you can look back and say, okay, which courses did I actually enjoy? And I enjoy the number theory courses, and I also enjoyed graph theory and combinatorics courses.
Okay.
The number theory, I feel like I was forced to, because to get this pure math bachelor degree, you actually need to take a certain number of fourth year courses, which are the same as graduate level courses. And they are very difficult, and they have many prerequisites. So, and they're offered in the fall of even years. So, or in the winter of odd years, and you're computing, oh, okay, what is odd? So, you know, like, it's not, it's, you need to like make an effort to take them, because you have to take all the prerequisites early enough such that you have this thing and you could
At the right moment.
at the right, when it's offered, not when the instructor is away or
So
something.
sometimes it can force you to be in a different field because
Yeah.
you somehow mess
So
up.
just like conveniently, it happened that it was possible for me to take all of the
And you
graduate.
wanted this particular ones.
Well, once you kind of are in the situation where you could take them and you can't take the analysis ones because you can't finish the analysis stream on time, then you're like, okay, I guess I'm now like an algebraic number theory person. I will now take all the courses they have on this.
But what I hear is that you found this experience of this course is quite enjoyable, I think.
Yeah, so the combinatorics courses, I found those very enjoyable.
Okay, and
I
yes.
think the best part is that the Department of Combinatorics and Optimization, they were very supportive. So at some point in my bachelor degree, I was kind of burnt out because I took a lot of math courses per term. And then at the end, I decided to pursue music, because I played flute throughout high school and also throughout university. And I decided, okay, maybe I would like to switch tracks and do a performance degree in music.
Oh, that would be the third major.
Yeah, so it was kind of achieved, but at the time, Waterloo was not granting the minor, the third minor or major that you have, if you already have two.
Okay.
So we didn't get this accredited.
Boo.
Yeah. But I think I could have, because I took all the courses that were required for it.
Okay.
And I have studio hours because I took private lessons. So this was like a thing that I was very devoted to towards sort of the end. We have 5 years of undergrad there, so there's a lot of space to do this.
Okay.
And then, yeah, and in the end, it didn't really work out. And yeah, there was some time when I didn't know, okay, what should I do now? And the CNO department was very supportive. So someone came and said, you know what you could do while you figure out your life? A master's in, in CNO. We could, arrange this. And then you could apply. This could be a thing. And yeah, so I did that. And it turns out, which I didn't really have this experience during the undergrad, I turned out to be much better as a master's student because there was research than as an undergrad.
Do you find research easier than studying?
No, I don't find it easier, but I find it more interesting.
Okay. I can understand that.
Yeah.
Okay. And then this seems, and then I guess there was something like you went to master, the next thing happened that you enjoyed the research.
Yeah.
And then you decided to go for academic career.
Yes.
So I'm curious, were there any like critical points along this journey, like still doubts or similar, like flute, not flute again, or like in general, I'm asking for something like, was there a critical moment and maybe a lesson that you wish that people knew?
There is, but it didn't happen to me because
What didn't happen to you?
like it's a lesson that kind of happened to me naturally, and other people didn't have time to try it.
Okay, what's that?
Having jobs.
Having jobs.
Yeah.
What about having jobs?
Like you should try it.
Having
It's
jobs.
like a thing. Like yeah.
Outside academia or inside
Yeah.
of academia?
Outside academia.
Outside academia.
To see how the workplace works and what kinds of things people do. So the reason why the undergraduate degree at Waterloo is 5 years is because it's cooperative education. So you have work terms and academic terms. And in total, you have 8 academic terms and 6 work terms. And these work terms are 4 month periods. That is the same length as an academic term, where you work full-time at a company or...
Like an internship or something?
Yes, but these are co-op positions, so they're full-time every day. They're 8 hours a day, and you are like a normal employee.
So like more
approximately.
organized, more systematic internships with connection with university.
And it has to be
Okay.
paid.
And it must be paid.
at
Because
the
any
scale
internship should be paid.
No, but you can also...
That's a good practice,
But
to pay people for their work.
It is a good practice, and I agree that, but there are also like unpaid internships that you hear of, and this is actually not allowed in this co-op system.
Okay.
So you have to like convince a company to hire you so much that they do it the normal
Okay.
way. And then,
Okay.
yeah, so I did do this.
Okay.
And it's a really great experience. So for just the interviewing for jobs, this co-op program at Waterloo has a whole building devoted to the interview process. So the employers, they come and they interview all of their candidates, and you go to this building, and there are like change rooms. There's like lots of, I don't know, people like 18-year-olds putting on their first suits.
And you get also help with like
Yes,
how
you
to
get
choose suit, how to
Yes.
navigate,
How to shake
what
hands.
to say.
I
Oh,
remember like there were like many sessions you have to go
that's
to
incredible.
them. Yeah, and you think this is maybe a waste of time, but then you go to the interview and
No.
you're like, no, it was not. Okay, this was great. And yeah, and it's like an airport. Like your name shows up on a screen with a room number eventually, and you're like,
Departure
okay, oh
gate
my god.
5.
Yeah. No, we had many training sessions where they explained to you should always, dress up. There are many people who showed up for what they thought was a phone interview, but it was in person.
Oh no.
And they were wearing, pajamas. So yeah. No, it's like a whole procedure that you go through this, and then I had some normal work placements. So I worked
And-
for
And what I can
as a
see
programmer
from this,
multiple
this is beautiful
Yeah.
initiative, and what I can see is that it is mandatory to have this and to go mandatory to have this internship.
yeah.
So
If you want to stay in the program.
yes. And also you have to go through preparations, you get support, and it is
Yeah.
mandatory. So you can like fail at some interviews,
Yes.
and then you still have to be given anyone.
No.
No?
So if you
Almost.
if you fail if you don't secure a position, then
But I guess once they see that
have
you're
some-
failing too many, they give you more support.
yeah. So they have a lot of support. They actually have a lot of
That's incredible.
Things.
That's incredible. The closest that I can recall, something similar to that, is just you get some reintroduction to society and some how to work workshops here at University of Amsterdam. But
Yeah.
it is not like the whole internship interviews. This is incredible. I can imagine
so
this
it's
to
like
be
even
useful.
in first year. But
forward
there were people teaching you what to wear.
What to wear, how to
Yeah.
behave,
Yeah.
what to pay attention
And
to.
also, like, people get positions at Bank of Montreal or at IBM or at, I interviewed at MapleSoft and many places. And there is Research in Motion, which is the BlackBerry company. It's also based in Waterloo. They hire a huge number of interns per year. So there is a wide variety of these positions, and the standard is different. Like some places are business or business casual or office. I don't know. There's like some levels, and then you have these adults that explain to you what does it mean if your workplace is business casual. What do you have to wear? And you're like, oh, I didn't know that.
Yeah. Yeah.
Yeah.
There's
So this is like
these
a
are
thing.
deep lessons which are
Yeah.
very simple to give.
Yeah.
And eventually, people like collect them like from scraps of some advices.
Yeah.
But that's
But this was, like,
very ineffective.
systematic.
But
There
that's
were
very
slides.
ineffective.
There were slides in shops also. They were saying, okay, this store is the cheapest possible store where you could buy something that passes for business casual, and you're like, oh yeah,
Whoa.
because like a first year student can't buy a $100 suit. Like,
No.
well,
Definitely not.
usually or multiple suits.
Especially that I believe that higher education is probably not free there.
It's not free, but it's about the same price as here, so it's not
Okay.
that expensive.
Okay, in Poland it's free for
Yeah.
Polish people.
So you could afford a suit.
I could afford, but still,
But many of
I got support.
my classmates at Waterloo, they could probably afford the suit, but they wouldn't want to buy the wrong suit.
yes.
Like they wouldn't want
Because
to invest money, and then
yes.
they show up and they realize, oh, this was not.
Yeah, uncertainty and anxiety is like something that we want to like. We can pay less or more to avoid it.
It removes like a lot of anxiety for pioneer students or students who are the first generation in their
Yes.
family to
Yeah,
have office
because
jobs.
they
or
do
to-
not have parents that will just tell you like what you're doing, do this, and like,
Yeah.
and you just go
This shirt
blindly,
is not. Yeah.
and you do not even think about that.
Yeah.
But
So
there are
then
problems with
there's
blindly
just-
following rules
yeah.
because you can easily not understand how to adjust if it's necessary.
Yeah, because you don't understand the actual rule. You've just been given snippets of what you think the rule is, and then you don't know how to adapt because you. Yeah.
Incredible. That's indeed a good lesson.
Yeah, so it's a whole procedure that I didn't realize that this was like I knew that it was a very good program. Many people recommended it. It was a lot of fun. All my classmates in it, many of them went on to have very cool careers, and we keep in touch and we talk about these things. And I had some placements where I worked as a programmer. But basically, I had some idea of what does it mean to work full-time as a programmer analyst. And this is like a very common career coming out of math.
Yeah.
And I knew that I preferred research to doing it.
Generically,
in a very
yes.
like solid way, because I also did research assistantships, and then I also did programming things. I also wrote the solution manual for a math textbook, high school math textbook. That was one of the jobs. And yeah, so due to actual experience, I knew that research was the best fit for me.
Whoa.
Because I tried the other things.
So once you decided to commit to that completely, you also knew the other options, and like there was no doubts, like maybe something else would be more suiting or something.
Yeah.
So it was, as with the suits, it was also anxiety reducing, and like I may have regrets, but I already know most of the facts about everything else.
Yeah. Like people I went to PhD with would say, oh yeah, like if this doesn't work out for me, I'm just going to be a programmer, it'll be fine. And I would just say, okay, I had a job where I programmed. I had a job where I programmed.
People say that, but they do not know what they're talking about.
Yeah, in like C# and also Fortran and some other, I don't know, some very complicated system. And I know I didn't enjoy it. I knew that it was fine. I kind of like got to a point where I was at peace with the challenges that I had to face, but I knew that research was much more fun. And the programming I do for research is much more fun than what I did there. So,
and here is a wonderful bridge to another question.
Yeah.
Because I know that you study graphs, but you also study graphs that are inspired by quantum mechanics.
Yeah, so one of the applications of algebraic graph theory is in quantum computing.
Okay.
And that's what I work on.
Yes. So first is like, how do you use graphs to study quantum things? Like quantum do not seem like to be dots and arrows.
But they are.
They are.
The
so
quantum computer
I'm
kind
not
of
a physicist.
is. Yeah, neither am I.
Okay, so
we're about to say some inaccurate stuff, and you're possibly going to get some YouTube comments which correct everything we say.
Well, that's life.
That's life.
So how do you start studying anything quantum using graphs? Like, how do you connect to this like origin of problems?
Well, so the thing is that it existed in the literature before, that you study quantum walks, which is a quantum process that evolves on an underlying graph.
I have no idea what's that.
It's I don't know, physically it's you have these things that will become qubits in your quantum computer.
Okay.
You have atoms or something, and then some of them interact with each other and not with others. Yeah. And this gives rise to a graph of interactions.
Yeah.
And you could say, okay, this graph, you have to draw it like in a plane, maybe. It's sort of limited. But that's not really true, because you could have the graph in 3 space. Because it's physics, they're not really limited to putting all their qubits on a plane. They could put it in 3 space. So then the class
if I
of
remember
graphs
correctly, 4 dimensions are enough for all graphs.
That's 4 colors is enough for planar graphs. Dimension, I think if you embed in 3 space, you can attain any graph, maybe.
Yeah.
So it's not
Okay.
It's not a restriction anymore.
Okay. So you have some states, then you write them as a graph, and then there naturally problems arise from physics to what you write about these graphs.
Yeah.
And then you use your eigenvalues, linear algebra, everything that you have at your hands.
Yes, to attempt to solve these things.
Okay. And then these graphs somehow relate to these qubits that are like to be programmed. And you already said that you have the experience with normal programming.
Yes.
Is it possible to program qubits?
Yeah, so I did program the IBM quantum computer
and
recently.
Is it like All people
It's
who
very
study
easy.
quantum graphs do?
No.
No?
So actually, no. People who do quantum computing, not everyone does this, and not everyone is familiar with it. So I did it over Christmas, because now that I'm an
Last
assistant
Christmas?
professor, this
24?
2024.
Okay.
Now that I'm a assistant professor, I don't have time to learn things. I have to like make time where I get to learn new information without being expected to write a paper on it immediately. This is like a thing. But anyway, I decided to devote some time to learning how it works to program on this IBM quantum computer. It has 127 qubits, the version that I used, and you can access it as with an open account. So you can run some amount of computations on this computer for free, for 10 minutes a month.
How many minutes?
10 minutes.
10 minutes per
10
month.
free minutes per
10
month.
free minutes per month.
But I've only used, I don't know, a couple of seconds per month.
What have you programmed?
I've programmed various small things. So the level of programming is very low.
Yeah.
It's like maybe remember is the wrong word. But think back to the days when people were programming with punch cards.
Yeah,
We're like in that era. We're in that era of
Okay.
quantum computing. We're not really programming where you can really program things. You kind of still are in the stage where you have a quantum circuit, like similar to a logical circuit with like gates and stuff, and you have to put the gates yourself to make it do some operation.
Okay.
So
it looks like you like what I imagine right now, that you're physically moving these qubits in space.
I don't do it, but I assume the quantum computer
Okay.
actually does something like this. I just access it through Python.
Okay. Have you programmed something that couldn't be programmed?
No.
In C# or something
No.
like that?
No.
Okay.
No. Well, okay. So it has 127 qubits. So
127?
qubits.
Okay.
So if you would evolve some operator on it, the matrix that you need to consider is 2 to the 127 by 2 to the 127.
That's a lot.
Yeah, it's a very so it's a very, very big matrix, okay? And if you couldn't mathematically just using not computers but write down what the output should be using logical principles, and because you understand what the gates do, if you couldn't determine that and you had to simulate this on a classical computer, then that classical computer needs to compute something with this 2 to the 127 by 2 to the 127 matrix. So it is very huge. And even squaring the matrix will take a very long time. It's so in that sense, we're at the sort of at a point where you could run things on it where you can't model it classically under some conditions. We don't know. But this computer is also very noisy, so its output is very different from what you predict mathematically.
What does it mean?
It's very noisy, it's very prone to error. So even if you say, okay, I put in this sequence of gates, I know that with 100% certainty, the output should be a 1 here and 0 everywhere else. Then the probability that actually comes out is not that high, depending what you did.
Okay.
And this is, in fact, a thing that I did program.
That's complicated to process.
Yeah, so one of the main problems I work on is called perfect state transfer. And the idea is that it's a subroutine for quantum algorithms, where suppose somewhere in your quantum algorithm, at the very base level, not at the level where you have compilers and stuff, but the very base thing of putting circuits and manipulating qubits, you want to transfer your state completely from one qubit to another qubit that is far away.
Okay. And by state, it's like the spin, color,
the
weirdness,
spin
and other things.
Yeah.
Okay.
Or you can think of it as
So
a
you
two-dimensional
pretty much want
vector.
to copy one value of
Yeah.
a variable to another place?
Yes, but
Okay.
cloning is not possible quantumly.
Okay.
So, but you can transfer, you can move it
Okay.
there, and of course you can do it. You can do it with a sequence of swap gates that just swap this thing to the next location, and then they go down. But this is very prone to error, because this operation, just imagine an error it's like a huge long sequence. If an error would occur early, then it would just not swap the right thing to the next one.
I can imagine that with my some vague memory of numerical algebra and doing computations and like keeping track of epsilons.
Yeah, so but it's a huge epsilon
exam.
currently. Yeah. So
I can imagine that this is that but harder.
Yeah, so this is sort of the thing that you could do, but then some people in quantum computing, they came up with this idea of saying, okay, so this is very noisy, but in the algorithm, if you have to move it, you have to move the state somewhere. That's a very basic operation that we should know how to do. So then in physics, we have this notion of a time evolution Hamiltonian, where on this group of qubits, you could evolve some process over time. And it would be nice if this process happened to bring the state from here to the desired location. So it's like a different thing. It's not swaps. It's like a thing that involves many qubits. Maybe it is more fault tolerant. It's time evolution Hamiltonian. And that's the quantum walks that we study.
So it is not like walking from place to place step by step. It's like navigating the whole space at once.
Yeah, it's navigating.
And then
somehow converging on the other thing.
at the end you want a particular result
with 100%
as doing
possibility.
this swaps with 100% accuracy.
Correct.
Okay, so that's something I somehow can imagine a bit, but what I can imagine is super mystical somehow.
Yeah, it is a bit mystical. It's
like going for a walk, but now I'm just moving the whole space to move myself to somewhere else.
Yes.
And
Yes.
And then out of nowhere, I'm like, I make a step maybe because everything like happened.
Yeah.
This is weird.
Yeah, it is very weird. But anyway, we did manage to, the field of algebraic graph theory, they did contribute to this development of PSD and the characterization and finding examples and characterizing whether or not it can happen. And this is an eigenvalue thing, really. It has to do with the eigenvectors of the underlying graph. And it's a nice thing. Vincent also has it for different types of quantum walks in his thesis.
And Vincent is your student?
Vincent is my PhD student, whom you know.
Yes, but people do not.
Yes, indeed. So now both of these things are implemented in the IBM quantum computer.
Okay.
So this time evolution Hamiltonian, it's not a native gate, but they can approximate it with gates that they have. And I implemented like a very small thing where it's a walk in a path of length 3 on 3, order 3 on 3 vertices. So it's 3 vertices.
So like you have like 3 qubits and
you have
want
3
to
qubits.
do 2 steps.
You want to move it. Yeah, so I did implement this in the IBM quantum computer using their time evolution Hamiltonian operator, and it kind of works with some error, but it's not that bad. And then the swaps, I also did this, and I did many versions because a swap is just a easy operator. It is also not a native operator.
But has this noise.
It has a huge amount of noise.
So 2 steps is probably like
2 steps was not that bad. It was, so I think it found it 75%.
How many steps do you have to do to get below 50%?
Not that many steps.
Not that many steps.
Not that many steps. So I did 100 steps. Because, or 99 steps.
As a test probably.
As a test. Yeah, because there's 127 qubits. So I could at least run a system that has 100 qubits. That seems okay. Right? 100 is smaller than 127, but the same order of magnitude, so it kind of demonstrates the size of the system. So I implemented 99 swaps from the top qubit to the qubit number 100. And then it was terrible. It was so terrible, I had to think about like statistics and how I could even look at the result.
Because you can like run it again and again and again, and then you get a distribution of stuff.
Yes. So
distribution of distributions?
Sort of. So every time it does a measurement. So I know that this swap thing, 100% of the time, I initialize one of the qubits to 1 by putting an X gate on it, the top one, and then I pass the state all the way down. So I know that every single time after the measurement that it performs, it should output a string of length 100, of which the first 99 positions are 0 and the last thing is a 1. I know this is the expected output.
Yes.
So we do this, and then the computer actually does it for me 4096 times. Like the power of 2, that's about 4,000. It does it that many times, and it outputs for me these 4,000 strings. And then you try to like analyze these strings. So I did this for the 100 swaps, and the correct string did not occur even once. In fact, no string occurred more than once.
Okay.
So,
but then the question is, like, as you mentioned, how to think about it statistically.
How do you even
is
do
it
this?
the correct, what you should expect to see?
Yeah, it was
because
kind of confusing.
I imagine that this is difficult to answer.
Yeah.
Is it what I see expected to be seen?
Yeah, I even doubted that I put the circuit wrong, but I checked. No, so then you can just measure the number of errors. And then, I don't know, it was a perfect bell curve around, I don't know, about 40 errors. Mm-hmm. Out of 100 slides.
Complicated.
And each qubit, it was about like 50% likely to measure 1, just separately. So it's pretty random.
Was that completely random, pretty much?
No, it actually...
Because 50% for each qubit being 0 or 1 seems like...
It's not every qubit 0
like
or 1.
we have no
there was
knowledge
a peak
about the
somewhere
system.
Else. Yeah. That is
Okay.
a problem.
Okay.
Yes.
So that's something for next people and you
Yeah.
to continue.
I even consulted Amy Musta, who is a colleague who is more familiar with statistics. She's in the stochastics group. And I asked her this output.
What happened?
Yeah, I did a thing. I expected this string all 4,000 times. It didn't occur. Here are the plots I made. What do you think? Is it purely random? How can I determine if it was random? And she also thought about it and said it's probably not random, but it could be, yeah.
But pretty much close. I don't know.
Yeah, I don't know.
Okay.
But you see, I think this is sort of what you expect because it is very noisy, and each operation, it kind of depends on the state being correct until that point.
Yeah.
Because the operation just moves the state from this qubit to the next one. So if it's already wrong on that qubit, it just moves an incorrect thing.
It's like with having a matrix and is it invertible or not, and you're changing
a little
numbers
bit,
a bit, and like it goes.
Yeah, and then then it just continues being non-invertible.
Yeah.
So this
or
is
sometimes
sort of,
it magically bugs to being invertible.
Yeah, that also happens.
Yeah. So
yeah, like for it to run completely correctly, you would need the whole thing to run without error. Because or magically such that the error happens to undo the previous error. So yeah, it's I think it is sort of because this chain, it is full of local operations, many small operations that completely depend on the previous one. It is very prone to error. So on a noisy machine that doesn't have error correction yet, this is sort of what you expect.
okay.
That it looks, difficult to distinguish from actual random data.
For the dreams of quantum graph theorists.
Well, it's not one problem, right?
Yes.
It's quantum computing and algebraic graph theory. This is a somewhat established connection. I think 10 years ago when we were starting out in this field with my colleagues and collaborators, it was very new at the time. Not 10 years ago, maybe like 13 years ago. It was like some of the first papers on algebraic graph theory or on quantum walks using algebraic graph theory. But now there are many papers and it's much more established. Many recent surveys of the area, for example, on distance regular graphs, they contain a section about quantum walks, about what things like people like me have done.
So this is like moving through this 100 steps without...
No. Oh yeah, with the time evolution Hamiltonian instead of the 100 steps. Yeah, about this problem of perfect state transfer.
So like jumping through all the steps.
Yeah, magically.
Yeah.
So yeah, this is now
And
part of the...
And this is like building software, this quantum graphs and Hamiltonian flows. So
not software like C++ kind of software, but the principle of software, yes. Like what QSoft does at CWI.
Okay.
So QSoft is this quantum software institute that I'm also a member of at the CWI. and they have software in their name, and this is the software. This is like in the philosophy of what they mean by software.
Okay.
Yeah.
What are your next goals in mathematics?
Yeah, so I have many projects that are ongoing. I would like some more of them to progress towards their endpoints, to be more finished. And I have a backlog of papers to write. So I feel like the goal at any time is just to eliminate the backlog and get caught up and succeed in surviving. And
Okay.
continuing to teach my courses and supervise my students as required. So this is already like a lot. Yeah, and then to have goals on top of that is sort of area specific, where you say, okay, specifically I want to think about these problems and so on. So I think the theme of the next research direction I want to do is things with eigenvalues of directed graphs, which is also what I started to do during my PhD. And there we developed some other matrix that you could use to record the adjacencies instead of the adjacency matrix, so that you could get somehow more information out of it, because you could represent it with a Hermitian matrix. So I kind of want to go back to this now that I've used similar techniques in other fields. I want to go back to this sort of thing. There are many open problems in graph theory that involve directed graphs. And sort of the analogous problems, which were for undirected graphs, they have algebraic approaches, where you could say, if this were true, what would be true about the eigenvalues of these graphs? And then you could prove that statement. So it's like an algebraic relaxation of whatever combinatorial fact people have. And yeah, so that's a thing that is less developed for the directed graphs, because there you cannot really say much about the eigenvalues and eigenvectors. So this is the next sort of big direction I want to shift to.
I wish you good luck.
Yeah.
And thank you for being here. It was wonderful to having you here.
Great. Thank you.